Welcome back to the lab, everyone. If you've been following our Embedded Systems Explainer series, you know we've already tackled the basics of sensor polling. But today we're taking it up a notch. We are moving way beyond basic polling and getting into professional-grade engineering. Consider this explainer your ultimate playbook for mastering DHT sensors, specifically the DHT-11 and the DHT-22. We're going to dive deep into the hardware protocols, uncover some seriously advanced software optimizations, and figure out how to build robust systems that absolutely won't fail you out in the field. So, let's jump right in.
Here's our game plan for today's masterclass. 1. Hardware, pins and protocols. 2. The sensor showdown, DHT-11 versus DHT-22. 3. Mastering the DHT new library. 4. Optimization and advanced settings. 5. Troubleshooting common sensor errors. And finally, 6. Real-world embedded applications.
All right, let's kick things off with Section 1, Hardware, Pins, and Protocols. When we look at the physical breakdown of the DHT-11, you'll immediately recognize that classic blue housing containing the chipset and a polymer capacitor sensing element. In the standard layout, pin 1 is your digital signal for the one-wire protocol, pin 2 is your VCC or 5-volt input, and pin 3 is ground. But listen, here is an absolutely crucial tip for your workbench. If you're using the 3-pin KY-015 breakout board, the middle pin is VCC. But if you grab a raw 4-pin DHT-11 module, that third pin is actually not connected. You literally always have to double-check your datasheet or you're going to risk a short circuit for sure. Now, getting into the one-wire communication protocol mechanics, it's important to understand that unlike basic analog sensors, the DHT series communicates digitally. To ask for a reading, your microcontroller basically has to knock on the door by pulling the signal line low. Standard datasheets will tell you to pull the line low for greater than 18 milliseconds, but highly tuned implementations actually use a precise 16 millisecond delay. This ensures an accurate reading while shaving off valuable processor time without dropping the handshake. The sensor then pulls the line low for 80 microseconds and high for 80 microseconds just to acknowledge. After that little dance, it spits out a 40-bit data packet with your humidity, temperature, and a checksum. This timing is so incredibly precise, which is exactly why standard baseline libraries sometimes choke if your microcontroller gets interrupted. Moving right along to Section 2, the sensor showdown, DHT-11 versus DHT-22. When we put these specifications side by side, it's pretty clear where each shines. The DHT-11 is fantastic for your basic, indoor ambient readings. It's cheap, it's reliable between 0 and 50 degrees Celsius, and it gets the job done. But deploying a DHT-22 becomes an absolute necessity the second your project needs negative temperature readings down to negative 40 degrees, or if you need high-precision decimals. The DHT-22 gives you sub-half degree Celsius accuracy and covers the entire 0 to 100% humidity range. Basically, if you're building a precision climate chamber, the DHT-22 is your heavyweight champion. Let's dive into Section 3, Mastering the DHT New Library. So what software are we running? The Adafruit DHT library is the industry standard. It's everywhere. But it requires strict object initialization. You literally have to hard-code exactly what sensor you're using with a hashtag-defined statement before the setup loop even runs. On the flip side, we have Rob Tallart's DHT New Library. This is a remarkably robust option because it features automatic sensor recognition. It actually figures out if it's talking to a DHT-11 or a DHT-22 on the fly. Plus, it has way better error handling, letting you use functions like set suppress error to neatly filter out those annoying -999 glitch values from your data logs. However, out in the real world, auto recognition isn't entirely flawless, mostly due to a funny little KY-015 quirk. Remember that KY-015 module, the DHT-11 on a breakout board? Well, it actually wakes up slightly faster than a standard raw DHT-11. Because it's so snappy, the DHT New library's auto-recognition can sometimes get tricked into misidentifying it as a DHT-22, which totally messes up your data conversions. To get around this, you have to manually override the auto-detection by calling setType11 directly in your setup loop. Honestly, it's knowing these tiny, obscure nuances that separates the novices from the master engineers. Okay, Section 4, Optimization and Advanced Settings. The DHT New library really opens up the hood and gives us incredible control over sensitivity and configuration. First off, you can use Set Temperature Offset to apply a first-order linear calibration right there in the class, so your specific hardware perfectly matches real-world baselines. Also, this is huge. As of version 0.5.0, the library seamlessly handles tricky negative temperatures. It detects the internal representation your specific DH22 uses and automatically picks the correct math algorithm. For battery-powered IoT, you can use power down and power up functions to save precious juice. And the coolest part? If you eventually upgrade to the AM2320X series sensors, you just call Type 22 and the library handles the rest, because the protocol is perfectly identical. Let's talk about efficiency for a second. 20 plus milliseconds. By utilizing the last read function within the DHT new library, you can check exactly when the sensor was last polled. If it was recent enough, your code just reuses the cache temperature and humidity values instead of forcing a brand new hardware read. Skipping that redundant read saves you 20 plus milliseconds of blocking time on a DHT11. And to put that into perspective, in embedded systems design, freeing up 20 milliseconds of processor cycles is a massive, game-changing efficiency gain for running your other tasks. Moving into Section 5, Troubleshooting Common Sensor Errors.
If you've spent any time with a DHT sensor, you have undoubtedly stared at NaN on your serial monitor. NaN stands for not a number. Why does this happen? Well, think of it like rapid-firing complex questions at your boss before they've had a single sip of morning coffee. They're just going to panic and shut down. The DHT11 physically requires a 2-second delay between readings to properly process the ambient air. If your main loop runs too fast and you don't pace it, the sensor drops the data packet, and your microcontroller just throws up its hands and gives you a NaN. Pace your code, respect the hardware's physical limits, and that NaN error completely vanishes.
Now, what if you aren't getting NaN, but your sensor is just completely stuck reading 99.9% humidity? Our source materials point out that this is almost always a voltage mismatch. For instance, if you are feeding a 5.3-volt VCC into an AM2301 or DHT sensor, but your data handshakes are happening at 3.3 volts, like on an ESP8266 board, the logic lines just get completely overwhelmed. Lowering that VCC to actually match your logic board resolves the overflow immediately. Rule of thumb, always check your datasheets for voltage tolerances. Finally, Section 6, Real-World Embedded Applications.
Let's tie everything together by looking at an application-oriented setup. In a clean breadboard implementation, the 5V power and ground need to be precisely routed, with the data signal going straight to a digital pin on, say, an Arduino Uno. But pay attention to the code logic here. You must define your variables using the float data type. It is absolutely crucial. If you just use an integer, you're literally stripping away the decimal precision that you paid for with the DHT22. Using a float ensures that when you push that data out to an I2C LCD display, you are getting perfectly accurate, high-resolution environmental readouts. Because of their solid factory calibration and that robust one-wire digital signal, these sensors are absolute workhorses out in the industry. They're used heavily in greenhouse climate control, where balancing temp and humidity is literally life or death for the plants. You'll see them in industrial warehouses protecting sensitive inventory. But my absolute favorite application, and one detailed extensively in our sources, is combining a DHT sensor with an SD data logger shield and a real-time clock or RTC like the DS1307. That combo lets you build a completely autonomous device that continuously writes time-stamped environmental data straight to a text file for months on end. It's brilliant.
So we've gone from the raw pins and microscopic 16-millisecond timing of the one-wire protocol straight through to advanced library calibration and finally into full-scale industrial applications. You officially have the embedded engineer's playbook for DHT sensors. So I'm going to leave you with this. How will you implement this robust fault-tolerant sensing logic in your next IoT environment? Take these masterclass techniques, head back to your workbench, and start building something incredible. Catch you next time.
Welcome to this explainer. Today, we're taking a real builder's journey. We're going to dive deep into the KY-015 module and transform the DHT11 sensor from just a raw electronic component into a fully functioning, autonomous environmental data logger. If you're looking to monitor the physical world with serious precision and totally ditch those outdated paper logbooks, well, you're exactly in the right place.
Here is our roadmap for the build. We'll start with number 1, meet the sensor. Number 2, technical specs. Number 3, wiring the circuit. Number 4, required libraries. And finally, number 5, building the data logger.
Section 1. Meet the KY-015 sensor. Let's see exactly what we're working with here. What you're looking at is the KY-015 module. Honestly, it's an incredibly popular, super accessible starting point for bringing environmental awareness into your custom builds. Whether you're running an Arduino, a Raspberry Pi, or a microbit, this little blue grid is about to become your new best friend. Technically speaking, this is a combi sensor. And that's actually a brilliant name, because it perfectly describes how it packs two absolutely critical measurements, temperature and relative humidity, into one tiny factory-calibrated package. And that factory calibration? A total game changer. It means you get to completely skip all those headaches of complex initial setup routines. You literally just plug it in, and it tells you exactly what's going on in the room.
Section 2. Technical specs.
To use any hardware effectively, you've got to know its limits. And this tiny unit, it's surprisingly resilient. It handles environments from a freezing 0 degrees all the way up to a sweltering 50 degrees Celsius, and it tracks humidity from a dry 20% up to a muggy 90%. Plus, it runs on a standard 5 volts, so it drops right into your typical microcontroller power rails without any extra hardware. All that data gets sent seamlessly over a streamlined one-wire protocol.
But, okay, here is a crucial detail. 2 seconds. That is how long this sensor takes to take a slow, deep breath. Because of its low sampling rate, you're only getting a brand new reading every 2 seconds. Now, at first glance, you might think a 2-second delay is a drawback, right? Actually, scratch that. This limitation perfectly defines its core strength. This isn't the sensor you use to instantly shut down a jet engine the millisecond it overheats. No, it's built for the marathon, not the sprint. It's optimal for continuous, long-term monitoring. Think climate control systems, tracking a greenhouse across a changing season, or monitoring moisture in a massive warehouse. That's exactly where this sensor shines.
Section 3. Wiring the circuit.
So now that we know what it does, let's wire it up. If we flip the module over and check out the intricate circuitry on the back of the board, it actually distills down to just 3 external connection pins. Looking left to right on most standard models, they're labeled with an S, a middle blank space, sometimes a V, and a minus sign. And wiring it is an insanely simple 3-step process. Step 1, hook the S, or signal pin, to a digital input on your Arduino. Pin 2 or Pin 7 are absolute classics in the community. Step 2, connect that middle pin straight to the Arduino's 5-volt power supply. Step 3, take the minus pin and wire it to your Arduino's ground. And boom, that's it. Your hardware is officially bridged.
Section 4. Required libraries.
With the hardware locked in, we need software that actually understands how to parse that one-wire data stream. Trust me, we do not want to write that complex translation code from scratch. Luckily, the open-source community has totally done the heavy lifting for us. The Adafruit DHT sensor library is a massively popular choice with an MIT license. Then there's Rob Tillart's DHT new library, which is incredibly clever because it features automatic sensor recognition. It just figures out if you're using a DHT11 or something else all on its own. And if you're venturing into Raspberry Pi or Python setups, the Adafruit CircuitPython DHT library has you completely covered. By just injecting this single, simple line of code, include dht.h, right at the top of your Arduino sketch, you basically unlock all the sensor's capabilities instantly. It handles all the crazy timing and data parsing automatically behind the scenes. Section 5. Building the data logger. Let's put it all together. This is the ultimate payoff. We're going to build a standalone monitoring machine that can completely replace old manual logging systems. We're talking an Arduino Uno R3 paired with our DHT11 sensor. Then, we add an Adafruit data logging shield to get a real-time clock and an SD card interface, meaning we can store years of data. We'll top it off with an RGB LCD shield for the user interface. And because we're makers, we can easily add on an optional light sensor on analog pin 3 and a voltage divider on analog pin 0. What's really brilliant about this specific shield configuration is the pure efficiency. The data logging shield sits there effortlessly handling SD storage and using its real-time clock to timestamp every single reading. But the RGB LCD shield, that's the real magic. It gives you a full 16 by 2 character display and 5 buttons, but it operates over just 2 I2C pins. Why is that a big deal? Because it frees up your other precious Arduino pins. That leaves your analog inputs wide open for extras, like that light sensor to tell you if a secure case popped open, or a voltage divider to alert you to a facility power failure. So, you now hold the complete blueprint to measure, record, and log the physical world for years on end. You know the hardware, the wiring, the open source libraries, and exactly how to integrate it all into a robust data logging machine. The only question left is, now that you have the power to digitize your environment, from greenhouses to server rooms, what environment will you monitor with your new data logger? Thanks for hanging out with me for this explainer, and happy building!